Hi, let's look at some integration, shall we? Okay, so I've drawn a curve on the board. Remember what it's called? It's called a cardioid. Okay, remember it's a heart just drawn like this. Okay, and the general equation of one of these cardioids is I equals a 1 plus cos theta. Okay, now as you can see, I've already gone into mode of drawing the axes like horizontally and vertically. Okay, just 'cause it's easier. Okay, just don't ever call them x and y. So theta is 0, theta is pi over 2. Okay, pi and 3 pi over 2 and so on. Okay, and you can quickly memorize or work out what these values here are. Okay, so when theta is 0, you've got 2a. When theta is pi over 2, you just got a, and then it's the same with this as well. Okay, and just remember why it's reflective about the initial line there. Okay, remember, because the result that cos negative theta, the same as cos positive theta. Very, very handy result to remember that. Okay, so it's got a line of symmetry about the initial line. How does integration work? Okay, how does integration work? Well, first it depends which part of the curve you want. Okay, do you want to find the area around all of that? Okay, do you just want to work out the top half? Okay, do you just want to work out this little bit in there? Do you want to work out that bit and that bit there? Or do you want to work out maybe the integral between here and here? Okay, I'm going to start with that because it's a good way of looking at it. Okay, right, the way that integration works in polar coordinates is this. Okay, suppose you've got a curve and just draw out a cardioid. There we go. And what you're doing is we're integrating with respect to theta, as you can see, because you've got r equals a 1 plus cos theta, so you're going to be integrating something with respect to theta. Okay, what that means is it's depending on what the angle actually is at the time. Okay, and the angle increases like this, doesn't it? All the way around from 0 through to 2 pi. Okay, that's what it does. So what we do is we call it a sweeping area, the area that is swept out around this path that I'm tracing here. Okay, so if you want to find the area around all of that, what you do is you'd integrate between 0 and 2 pi as your limits. Okay, if you only wanted to find half of it, like for example the top half, you do it between 0 and pi. Okay, if you only want to do it between here and here, you need to know what angles they are. It might be that is theta is pi over 6, that might be theta is pi over 3, something like that. Okay, in which case you're working out that area there. So just a reminder, polar coordinates, it's not rectangular. Okay, Cartesian coordinates, they are rectangular. Remember I mentioned about the summation of an infinite set of rectangles to find the area on a Cartesian graph. With these, they're not rectangular. Okay, they are circular, really. Okay, circular. Okay, or sectors of circles. Okay, and because they're sectors of circles, that helps us with how we're going to integrate. Okay, because we need to have a general method, a general formula for integrating. It's not just saying, right, let's integrate that. There's a bit more to it than that. Okay, each time you integrate, you are effectively doing an infinite sum of sectors of circles. Okay, and those sectors of circles, they can be changing radius and changing angle. Okay, so you can see it's not a circle, is it? Okay, so the radius is always going to be changing. Okay, and that radius is always changing with respect to theta. Okay, what we can do is we can divide this shape up into as many different sectors of circles as we want with varying degrees of r. Okay, and what I'm going to say is I'm going to label that as r. Okay, I'm going to label that angle there because it's changing. I'm going to label that angle there as delta theta. Okay, and do you remember the formula for the area of a sector? Yeah, very good. That was 1/2 r squared theta, wasn't it? So 1/2 r squared delta theta, that would be. Now, to get the exact integral, we need to divide this up into an infinite number of sectors. So what we're saying is, as delta theta tends towards 0, what that means is, of course, these lines are getting infinitely close together. As delta theta becomes infinitely small, tends towards 0, and so basically all of this gets filled up completely, and this becomes 1/2 r squared d theta. So our formula is 1/2 r squared d theta. Okay, and that's your general formula for the area in polar coordinates, okay, which is kind of nice. Okay? So whenever you've got a graph drawn, okay, if you've got an equation given to you, just integrate using half r squared d theta, okay, and that gives you your answer. And I'm going to do this with you now to show you exactly how that works. I'm hoping that made sense here. So let's do this then. So the integral of that, so what I often do is I put the half outside the integral bracket, okay, and then r squared, which means you've got to square that, of course. So a squared 1 plus cos theta squared d theta. That is it. That's your method. That's what you've got to do. Okay. It also depends on what you want to do. Okay. Do you want to work out just that area there, or do you want to work out the area of the whole shape? Okay. Shall we just begin by doing the area of the whole shape? Yeah. Maybe worry about the limits afterwards. Okay. We'll do the integral first. That's the exciting bit, isn't it? Okay. How would you integrate that? Maybe just pause the video and have a go at it. But what I would do is I'd also take out the a squared actually, because that's also a constant term. Okay, and yeah, I'd expand the brackets. So you'd have 1 plus 2 cos theta plus cos squared theta d theta. Yeah, good. Okay, and then we just integrate that, and hopefully remember how to integrate cos squared theta. Okay, shall I put it here? Yeah, let's put it there. Okay, so which identity do you want to use? Do you want to use 2 cos squared theta minus 1? Is it to cos 2 theta? That's the identity I'm going to use, you see. Okay. If you're not using that identity, which one are you using? This is the one. Okay, remember in the blue textbook. Okay, so let's just make that the subject. So cos squared theta is equal to cos 2 theta plus 1 and then divided by 2, isn't it? Okay, I suppose I could have put it on this board, but yeah. So anyway, let's just leave it. This is awkward. Where did I put it? I'll put it there because I'll, yeah. So half a squared integral of, let's add these things together, shall we? So cos squared theta is going to be a half cos 2 theta plus a half. So 1 plus a half. Can I write in 3 over 2 there? Of course I can write 3 over 2 there. I'm sure you won't mind. And then that's going to be 2 cos theta. And then the cos squared theta bit, so that's half cos 2 theta, don't I? Plus a half cos 2 theta. Yeah, does that make sense to you? Hoping so. So I'll just put it there, you see. So the 1 plus 2 cos theta plus cos squared theta, that's that. 1 plus the half there, 3 over 2, and then the half cos 2 theta. Yeah, good. Great. And then we just integrate that. So what are we going to get? Now you might wonder at this stage, well, why don't you bother taking a half out? You've still got fractions. It's just what I do. Okay, it's just what I do. You don't have to. Because the answer's going to be the same, isn't it? Let's face it. So 3, also maybe you pause the video. Or maybe you didn't. You don't need me to tell you. 3 over 2 theta, and then this one here, what's that going to be? 2 sine theta, and then this one here is going to be plus a quarter sine 2 theta. Do you ever differentiate by checking your answers? I'm doing that in my head all the time because I'm always a little bit paranoid. I'm integrating them wrong sometimes. Like these ones, I'm like 2 sine, right? Yes, that's right. This, do that? Yes, that's right. Okay. Yeah, so you should have that. Okay. As long as you get down to that stage, you're ready to substitute limits in. Okay, so let's just do that, shall we? So what did we say? You want the whole of it? Okay, well, fine, yeah. So you could substitute 0 to 2 pi, yeah? Okay. There are alternatives with these types of question, okay? Because of the symmetry, okay, you could substitute in 0 to pi, then double it. That's another possibility, okay? Why does that work? Because if you just put in between 0 and pi, you get all of that area, you see. That's swept out between there and there, so you get all of that. And if you've got all of that, you just multiply it by 2 and you get this. Okay. There are no negative areas in this, incidentally. Maybe I should point that out. Okay. Remember in Cartesian form, it's like we've learned a lot of things about that. In Cartesian equations and graphs, we've learned that above the axis area is positive, below the axis area is negative. It's not like this at all. Okay. So if you do put in between 0 and 2 pi, you will get all of that as one positive area. Okay. Now the advantage to doing between 0 and pi, yeah, and then doubling it is this. You can then just double that, and so you don't have the half anymore. Okay. That's sometimes the reason why I'm in the habit of putting the half outside, you see, because you can sometimes do that sort of thing. Okay, it makes it a bit easier. All right. Maybe if you want after this, you put the half back in and you try it between 0 and 2 pi. Okay, it will work. If it doesn't, you've made a mistake. Go back and do it again, but it will work. Okay. Now let's just follow this through. The thing with these things is you've got to put the limits on every integral sign and every one of these integral brackets there. Okay. So let's just do that. So can I squeeze it in? Ooh, don't know. We'll see. It's looking dodgy. I might be able to. We'll see. So 3/2 pi. 3 pi over 2. Sine pi is 0. Sine is 0. Yes, I like that. I like it when that happens. Okay. Then 0. So that's got to be subtract. 0, 0, 0, 0. Oh, I can put it all on one line. Yeah, you find that? It's quite easy, isn't it? Sometimes they do end up easier than you think. So 3 pi over 2, a squared. Okay, so 3 pi a squared over 2 is our answer, which is kind of nice. Okay. Yeah, so yeah, that's that. It's kind of nice to know as well. Just check. We are still, yeah, you were still recording, tired. I hadn't listened and I just, it wasn't important. It was just one of my favourite questions where the video stopped working with the lemniscate. It just had to stop working during that, didn't it? Anyway, yeah. Anyway, so what that means is the area under all of that is, you know, this. Okay. Play around with it if you want. Okay. So like I said, if you wanted to work out the area between this bit here, when you got theta's pi over 6, and this bit there, theta's pi over 3, and to get that area, you can do. Yeah, you can. You've got your integral done. You just change the limits, okay, and you get what the answer is for that. Okay. While I'm still on this example, with all of this drawn out, okay, how would you work out the area of, let me show you the info, so you can think about it. How would you work out that? Just think about it while I rub the rest of this off. Yeah, did you get an answer? So if you just wanted that bit in there, how would you do it? Well, clearly you've got down to here. So in exams, that's where most of your marks are, isn't it, of course? The limits bit is just a tiny bit, okay? You might think, oh, it's only the actual answer, you know. Yeah, but in terms of the working, that's worth more marks, isn't it? What limits would you substitute in there to get this area there? Can you tell me? Well, just think about it, okay? Sometimes the pen comes in handy, okay? So you don't want any of that, do you? So you don't need between 0 and pi over 2. It starts when theta's pi over 2, and it ends when theta is pi. Yeah? So you put pi over 2, pi. Okay, you see that again? So it starts from this line here, doesn't it? Theta's pi over 2, and it works all the way around to this line there when theta is pi. So you just substitute. Maybe you just do that as well and see what answers you get. Okay. Hopefully you get lovely answers. Okay, but you should get correct answers. Okay. Remember to be in radians. Always be in radians. Okay. At this stage, you're very rarely in degrees, are you? Okay. It's kind of a novelty, isn't it, when you're in degrees now? It's like, oh, there's a degrees question. Let's just put the calculator back into degrees. Yeah. Good. Hope you enjoyed that. It's kind of fun, isn't it?